Day 118, the speed and energy of light waves. The purpose for the day will be to learn equations that determine the speed and energy of light waves. The relevance, these are basic concepts of optics. Success, you'll be able to correctly choose the equations to use and substitute correctly to get an answer. Tonight you have homework 118 to do, and we have a quiz next class. You want to take some time to see this video, go right ahead. New material. In previous chapters, we learned the relationship between velocity, frequency, and wavelength as being the equation velocity equals frequency times wavelength. Does this equation apply to light waves? Yes, it does. All waves are going to behave in the same way. The speed of light in vacuum is a special thing. It is approximately 300 million meters per second. It's actually a little bit less than that, 299 million and something, but we're just going to always round to be 300 million. Number 3, this speed in vacuum is the same no matter what the medium is doing. So they have measured the speed of light when they shine the light going on Earth, north and south. And then they measured the speed of light with it going, with the light beam going east-west. Now, with the light beam going east-west, it gets some additional velocity, so to speak, from the rotation of the Earth. At least that's what they thought would happen. But it turns out that no, it's the exact same, no matter what. So if you were hitting a baseball, it makes a difference if you are going with the wind or against the wind or across the wind. With light, it doesn't make any difference at all. Number 4, the speed in vacuum is special because nothing can go faster than the beam of light. It's the speed limit of the universe, so to speak. Number 5, what happens to a spaceship if it uses energy to try to get faster than light? Let's say you had a spaceship that had an unlimited amount of fuel for some reason. And as it starts off and gets faster and faster, it is turning the chemical energy of the fuel into kinetic energy of the motion of the ship. But as you get closer and closer to the speed of light, the chemical energy does not add kinetic energy. Rather, it adds mass. The spaceship actually gets heavier. It gets more mass. It gets more massive. So that's another indication that mass is just another form of energy. Number 6, when light goes through different mediums, it will change speed. The denser the material, the slower the light will go. So when light goes from a vacuum to a clear material, the speed will go down. When light goes from a material to any more dense material, the speed will go down. So as you go from air to water, light slows. As it goes from water into a diamond, the light is going to slow down. The opposite is also true. As light goes from a material to something less dense, the speed will go up. The refractive index is a measure of how much light slows down when it goes from a vacuum into a medium. Its equation is N equals C all over V. The C is that special speed of light, 300 million. Sometimes you'll see it in scientific notation, 3 times 10 to the 8th, and that's in meters per second. The V is the velocity in the medium. C is the speed of light in vacuum. N is the refractive index. It's a special number that's going to be assigned to every substance that light can travel through. A ray of light goes through oil at 160 million meters per second. What's the index of refraction? So the raw equation is N equals C over V. We're looking for the index N. The C is 300 million. The V is the 160, that's the velocity in the medium. And I type that out. 300, 1, 2, 3, 1, 2, 3, divided by 160. 1, 2, 3, 1, 2, 3. 1.875. Note, the refractive index is unique for each wavelength and each medium. The chart below is for light with a wavelength of 589 nanometers. Use this chart for all your homework problems, unless stated otherwise. When calculating equations, you can convert the wavelength of 589 nanometers to be 589 times 10 to the negative 9th meters. This is not proper scientific notation, but it will calculate just fine. How much does light slow down when it enters water at 20? So here's water at 20. And we have an n being 1.33. So I put that into the equation. Here's the equation. The n becomes 1.333. The c is the speed of light in a vacuum, 300 million. And the v is the velocity in the water. Now notice the v is at the bottom. We're not going to just simply divide both sides by 300 million and call it good. I'm going to make this a proportion. You can cross multiply and divide, or you can flippity-flop the diagonals and end up with 300 million divided by 1.333. 300, 123, 123, divided by 1.333. And I get the velocity is 225.056264. Well, just simply saying 225 million is enough. So it slowed down from 300 million down to 225 million. You could say it slows by 75 million. Different ways of saying it. What equation tells you if the energy of a wave when you know the frequency? That is E equals hf. E is the energy, F is the frequency, and H is a special number, 6.62 times 10 to the negative 34th. That number will always be given to you. You do not need to memorize it. It is called Planck's constant. You do need to memorize that name so that if you ever needed to look it up on the web, you know what to type in the Google search. Now, if you know the wavelength, it's a different equation. Here we have the equation with wavelength that we've studied before. Velocity equals frequency times wavelength. And let's solve this for the F. So I divide both sides by wavelength. So those cancel out. And I get F equals velocity of the wave divided by the wavelength of the wave. That can go in for this F here in our equation. And so we'd get E is equal to H V divided by wavelength. The variables represent E is the energy, and that's in joules. The H is 6.62 times 10 to the negative 34th. The V is the velocity in meters per second. And the lambda is the wavelength. Wavelength in meters. This F here, I'll write it down. F is the frequency in hertz. That's the number of waves per second. Okay, find the energy of a 589 nanometer light moving in a vacuum. So nanometers, that is a wavelength. 589 times 10 to the negative 9th meters. So E is equal to HV over lambda. The H is 6.62 times 10 to the negative 34th. The velocity, light moving in a vacuum, that's the 300 million. And then we divide it by the wavelength, which is the 589 times 10 to the negative 9th meters. You got to use the plain old meters version with a negative scientific notation. So I type that into the calculator. 6.62 exponent negative 34 times 300 300 million divided by 589 EXP, or the EE button, negative 9. Now I use the scientific notation, but if you don't use that, you're going to possibly make a mistake. You need to use parentheses. Hit equals, and we get 3.37 times 10 to the negative 19th joules. Find the energy of 589 nanometer light in 20 degree water. Well, the first step is to find the velocity. So we have to use n equals c all over v to figure out what the velocity of light is in that water. And we found that before, up here in this problem, 225. So the first step we've already done. The velocity is 225 million. The second step then is to use this equation. So the h I'm going to just type in here, 6.62 times 10 to the negative 34 times, if that's the h. Now the velocity is the 225 million. Then I'm going to divide by the wavelength, which is 589 nanometers. 589 times 10 to the negative 9th. And I get 2.52 times 10 to the negative 19th. You can watch this video here if you'd like. There's a couple there. And then we have some sample problems if you want more worked out. Here is a study guide for you for your quiz that's tomorrow. And on the next page we have the answers for those review questions.